All right, everybody, welcome. Oops, I gotta move that over. Okay. Oops. Sorry, I can't show that. That was messages. Let's do this. Let's see. Here we go. Okay, so here we go, everybody. Let me double check something really quick. Okay. Okay. Just double checking something. Okay, so let's see. We are all right, so sorry, I accidentally, let's see, that is the one I want. Okay, so we're in here. So we've got basically 3 class meetings left, including today. So you're getting very close. Remember that chapter 6 isn't going to have as much stuff on the, really there won't be much from chapter 6 on the final exam, just this very beginning stuff. The very beginning of chapter 6 will be on the final exam, area between curves, but the subjects that we cover after that, basically the stuff that we cover on Thursday, except for area between curves, I'm not sure exactly when we'll cover that. Anyways, let me make myself clear. Area between curves will be on the exam. The rest of the stuff in chapter 6 will not. So in fact, maybe it's easier if I show you in here for chapter 6. This area of regions in the plane, 6.1, will be on the final exam. 6.2 and later will not, but you need to know that stuff because, one, you need to get points for the homework, and also consumer and producer surplus is stuff that you need to know for the future. So when it comes up in your economics classes and stuff, you know what people are talking about. Annuities and money streams depends on what you're going into, but some of you might find that very important. And then these other sections are they're still important. I'm not saying they're not important, but some of them you won't use as much. Like probability depends what you're doing, right? Some of you, if you're in a, it depends. Just depends what, if you're going into accounting or economics or whatever. But 6.1 will be on the final exam. And if you look here, let's see, let me move this here. The practice final exam was posted yesterday, Wednesday. So like I had said I was going to post it Wednesday, it's up here. So if you click that, it's got the, here's your practice for the final exam. So I just want to reiterate, I always say this, I reserve the right to change problems to different things. So sometimes students go, oh, I only have to study this problem because it's on the practice, but other things are not on the practice, so I don't have to know those. That is not true. I could take one type of problem involving, say, logarithms and change it to a different logarithm problem, or change it from, you know, one part of the logarithm chapter to a different part of the logarithm chapter. Like, just make sure you know how to do everything. This is just a guide to get you started, to help you figure out where you're weak and where you're strong so that you can get that stuff done. So what I'm saying is, don't take the lazy approach that some people do and say, oh, I only have to know how to do the problems that are on this practice exam. That is not necessarily true. Okay, I reserve the right to change those problems to be different. I'm not going to give you a totally different exam that looks completely different. But, you know, sometimes students just get locked into, I only have to know these 12 problems and that's it. That is not the case. Okay. So we've got, let me jump into XYZ homework. We're finishing up chapter 5 today. Oh, that's right. Yeah. Sorry, I was thinking of my morning class when I was talking about something a second ago. Yep, so we're finishing up Chapter 5 today. That means we'll start Chapter 6 on Tuesday, and then we'll finish up Chapter 6 on Thursday. But again, you won't be responsible for the stuff we cover Thursday on the exam. You will be responsible for it for homework, but not responsible for the stuff for the exam. Only 6.1 and earlier do you need to know for the exam. Okay? And yes, there are going to be a couple problems. I think, actually off the top of my head, I don't remember. But there might be problems from earlier in the course on the final exam. Okay? I might throw one of those on there. Right. Oh, and speaking of which, your test is next week, so make sure you know when you're taking the test, when you're getting all of that squared away. Okay, so basically there's no time to move things back. If you don't get the test taken by Friday the 28th, then you're either going to end up with an F or you're going to have to get it incomplete. And 90% of the time students get incompletes, they end up turning into Fs. So avoid that at all costs. Okay. So, oh, and by the way, just so people know about incompletes have to be accompanied with like medical documentation. So, if you miss the test because you have COVID, that's fine, but you got to bring me documentation that you had COVID. We'll give you an incomplete. You can take the test in the fall, that kind of stuff. But none of that sounds good, right? So, just make sure you have your appointment set up. You're all squared away. You're ready to go. Those of you who are taking the test remotely, even if you're using the same place that you did for the first exam, send me a message to make sure I know exactly what your plan is. Okay? So still message me again. Okay, so with that, let's jump into the material. I don't see any questions coming up. So let's jump into material then. We have two big sections to cover today. We're covering improper integrals, which what I'll say about improper integrals is that if you're up to date with the information we've done in the class, and you understand your limits and you understand your integrals, then the biggest difficulty you're going to have with improper integrals is not the actual computations. It's with like understanding how to set the problem up. Once you get to where you can set the problem up properly, if you've been doing your homework and understand it up to this point, you should be good to go. Like if you're comfortable with the first half of chapter 5, then 5.5, the thing that's confusing is setting up the problem, but once you get that, once it conceptually clicks and you go, "Oh, I know how to set these up," then the rest is just kind of stuff you already know how to do. So it's really not that difficult. 5.6 is one of the most hated sections in the class. What I will say is I'm not saying it's easy the way we do it in this class, but normally when you hear people complain about integration by parts, they're kind of usually more talking about like the engineering calculus. They do problems in there by integration by parts that are just horrendous, and if you make one little mistake, things don't line up, and it's a pain. Like this integration by parts techniques that we're going to learn, for us in this class, you just do it once and then you're done. But some of those other classes, those like the engineering calculus classes, you have to use the technique like 4 times, and then it circles back, and then you get your answer. We don't have to go through all that. So if you've heard people talking about integration by parts being particularly scary, not the way we do it. We just do it for a few basic type of problems that apply to business calculus, right? So it's actually not too bad. There is a little bit of a formula you have to memorize, but it's actually not too bad either, right? You can memorize it. By the time we're done with lecture today, you could have that thing memorized. It's not like there are some pretty rough formulas in business calc. Like when we get down here in 6.3, annuities and money streams, usually those can have some pretty nasty formulas in them. Like formulas for annuities are just rough. I wouldn't expect you to memorize those. But the formula for integration by parts, you just need to know it. You just need to know how to do that, because people go, oh, well, can I have a cheat sheet or something? Like, you basically can't do the problem unless you know how that problem plays out. So you just need to know it. Okay. But like I say, it's not even a very hard formula. You can almost just get comfortable with it by just saying it. In fact, if you're having trouble with the integration by parts formula after today, here, like simple formulas, here's the best way to memorize them. Write them down 30 times, and while you're writing it out, say it, right? And you'll have it memorized by the and people go, oh, 30 times, I'm supposed to write it 30 times. That'll take you like 3 minutes. So it's not that hard, right? It's not a very complicated formula. So with that, let's dive in. I think I have this one already set up and ready to go. Okay, so let's take a look at the 5.5 homework, improper integrals. What do we mean when we talk about improper integrals? And those of you who are caught up are probably already looking at this and seeing where the issue is arising. It's that infinity. So there's a couple of different ways in which we can have improper integrals. They can be set up a few different ways. The good news is if you understand the basic concept of the improper integral, you'll have that flexibility to adjust to the different types of problems that you're working on. So again, don't try to memorize like, oh, when I see this problem, here's what I'm supposed to do. Just understand what's going on, and it's a whole lot easier to remember this kind of stuff. Okay, so let's see. It looks like I closed the book. I was looking at sort of getting everything set before class, but it looks like I must have closed the book here. Here is the issue with an improper integral. Sometimes, like, this sounds weird if you're not used to sort of these kinds of calculus ideas, or you're still getting comfortable with them. But you can have things that involve infinity that are still finite, which that sounds weird. Like, isn't that saying something's infinite and finite at the same time? Well, things can be infinite and finite at the same time. So take, for example, like on the x-axis, right? Take the length from 0 to 1. So you've got an x, a number line in front of you. From 0 to 1, that's distance 1, right? But how many numbers are there located between 0 and 1? There's an infinite number of them, right? There's an infinite number of numbers, including fractions and decimals and all that kind of stuff. There's an infinite number of numbers between 0 and 1. So even though you're talking about a finite length on the number line, there's an infinite number of things inside of that finite length. Okay? Just like if you have a rectangle and the plane, there's an infinite number of points that are inside that rectangle, right? So you want to get comfortable with this idea that things can involve infinity and still be finite at the same time. And sometimes it gets really, really strange, right? Infinity, starting with calculus, when you learn about infinity, it starts doing weird things. And the further and further you go taking, if you become a math major, you take all these math classes, every time you run into infinity, it gets a little bit weirder and weirder, right? Let's see. Basically, our improper integrals involve infinity in some way. There's a couple of different ways in which they can involve infinity. But if you understand the basic concept of what we're looking at, then you'll know how to set these problems up. So let's see. Improper integrals. We're going to set this up by looking at a very basic example. We've got an integral here. And we want to look at a situation where we go, let's see, I'm going to have to zoom out here a little bit. We want to look at the situation where we're talking about the integral from 1 to infinity. Right, so you can kind of see where we're going. We want the integral from 1 to infinity of 1 over x squared dx. And that seems weird. You can have something with infinite length, but then finite area, right? Like there's this weird object called Gabriel's horn, and it's got it's a mathematical object that has has finite volume in it, but an infinite area, meaning it would take an infinite amount of paint to paint the thing, but you could fill it up with water, right? That's an idea that's kind of strange, but it kind of relates to this kind of shape that we're looking at, where we're looking at something that's infinitely long, but the area that's in it is finite, okay? So here's the idea. We're looking at 1 over x squared, and we want to look at the interval from 1, so starting at 1, and then going to infinity. So if we zoom in here a little bit, we can start off by saying, well, let's go, instead of going all the way from 1 to infinity, because we don't know how to deal with infinity, right? Like, it's not a number. People try to use infinity like it's a number where they plug it into things. And sometimes we do that. We'll say the limit as x goes to 10 is infinity or something like that. But remember, we're not really specifying that it's a numeric value. We're describing how that thing is diverging. It's going to infinity, or it's going to negative infinity. That's really what it's telling us. We're not trying to give a value to it, because infinity is not a number, right? It's telling you something about the behavior of what's happening with your object. So the pattern that they have in the book here is they have us looking at different values of what we're going to call b today. We use lowercase b for this value. So we say, well, if we wanted to know about the area under this curve from 1 to infinity, which we don't know how to deal with, what if we just start looking at the pattern of things we do know how to deal with? So the area from 1 to 2. The area from 1 to 2. Okay. What about the area from 1 to 10? Okay. What about the area from 1 to 100? Okay. What about the area from 1 to b for any size b that we want? So basically what they're doing here, remember how we calculate area under the curve? You're going to take this function, you're going to find its antiderivative, and you're going to evaluate it here from 1 to 2. Here you're going to evaluate it from 1 to 10. Then from here from 1 to 100. So that's where those area values are coming from. It's from the area arguments that we did last time, that we did on Tuesday. Okay. Well, here they're saying, what if we don't pick a specific endpoint? We just call it, let me move this up here maybe. Go right there. What if they say, well, instead of calling this some endpoint and we keep picking specific numbers, what if we just say it goes to b? And then we could say, well, what if b was 1,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000? Or what if it's a 9 with a billion zeros after it, right? So huge, huge numbers. Well, then we could still look at that area by taking the area, equating it to an integral like we did on Tuesday, and saying it would be the integral from 1 to b, right? Our starting point of 1 and our ending point of b of 1 over x squared, because that's our curve. We're finding the area under this curve. Dx is equal to 1 minus 1 over b, right? That's what you get when you plug these endpoints in. So in this place, we can start to see, well, why did we get those previous values? Well, here it was 1 minus a half. Here it was 1 minus a tenth, gives you 9/10. 1 minus 100th gives you 99/100. So we can see what's happening here. As we extend b to be larger and larger and larger, we're getting 1 minus a tiny, tiny little number. Well, what happens when b is growing big? This whole term here is shrinking down small. It's getting very, very tiny, meaning if we start thinking about the limit then, well, what if we extend b to infinity? What's the limit as b goes to infinity? Well, then this term right here gets closer and closer to 0, and we effectively end up with 1 minus 0. So what we're seeing here is the area under the curve from 1 to infinity is 1 for this area under the curve, which seems weird. Again, we mean we have an area here that is infinitely wide, right? It's going down towards infinity on the x-axis. It has an infinite width, and yet the area under the curve is finite. That's kind of a strange thing to think about, right? You would think if you had a shape that had an infinite dimension, it went on infinitely forever in one dimension, that the whole area would have to be infinite. But this shows us it does not. Okay? So then that's basically how we're going to treat these things. When we want to find the area under a curve from some value to infinity, we are going to pretend like we're really only going to a finite value b, like we pick a finite endpoint b, but then we send b to infinity. Okay, that's the step that allows us to do this. And you might go, well, why do we go through all that? Well, it's because we can't plug infinity into a formula. Math doesn't work that way because, again, infinity is not a number. So we have to be able to plug a finite value into the formula, and the only way to do that is to use some placeholder b and then take the limit as b goes to infinity. Okay, that's the big idea behind what we're trying to do here. So for these types of integrals, if you want the limit, if you want to know the integral of this function from 1 to infinity, then you take the limit as b goes to infinity of 1 to b, 1 over x squared dx. And we just figured out that it was 1, right? But that's what you do, is you take the limit if you have infinity in there. Now, there's a couple different ways you break these down. Depending on the way that infinity is messing up your problem, you get around that in a few different ways. Okay? So let's take a look at these so that you'll know how to set these up. So we just looked at an example of the integral from a to infinity f of x dx. And we said, well, why don't we treat that as the limit as b goes to infinity of the integral from a to b f of x dx. That's what we just worked through. So step 1 is the one we kind of just saw an example of it. Step 2 basically says, what if we flip it over the other way, where we're going from negative infinity up to b? So we just kind of looked at show you on a graph here. We were just looking at, what if we start at some value here and move to the right forever? Well, now we're saying, what if we start at some value and we're coming from or we end at some value coming from the left? So you start at negative infinity all the way down on the left side forever, and then you come up to a certain value and stop. So you could imagine it's really kind of the mirror image of the problem that we just worked through a moment ago. It's basically the same thing, but just mirrored over on the graph. So we can see that this makes sense. We're going to now have a go to negative infinity, have a be our lower endpoint, and then you take the integral, and then once you've taken the integral and evaluated it from a to b, then you take the limit and send a to negative infinity. So if you understand part 1, you really should be able to understand part 2, because you're just flipping it over onto the negative side of the graph is basically all you're doing. 3 is a little bit different. We have to think about 3 in a slightly different way. So 3 says, what if we have the integral going from negative infinity all the way to infinity? So we're going forever on both ends. We're going forever on the left. We're going forever on the right. How are we going to handle that? And what this says is you need to break it up into 2 smaller integrals. Basically, like one turns into part 1 of what we got here on screen, and one turns into part 2. So instead of going from negative infinity to positive infinity, you say, why don't we go from a to c, where a goes to negative infinity, and then we've got a second integral that goes from c to b, where b goes to infinity. So you've kind of taken that infinite integral, where it's infinite in both directions, and you've split it into 2 integrals that are just infinite in one direction. Okay, and of course the c has to be between a and b, because we're picking a midpoint. I mean, it wouldn't make sense to do it otherwise anyways. If these limits exist, the improper integral is said to converge to the computed value. Otherwise, it converges. So we say it converges when you're integral, you get like a finite number value back, like 4/5 or 7/8 or 27 or something like that. Otherwise, it diverges if it doesn't go to a specific value. Now, this is kind of weird. This shows like an interesting cutoff for mathematics. So notice how we just looked at the integral of 1 over x squared from 1 to infinity, and we showed that the area is 1, right? Because as b goes to infinity, you get 1 minus 1 over numbers that are going to infinity. This becomes 0. You get 1. So it's kind of weird. This pink area, as the pink area, this b goes to infinity, the area is 1. But if you just change this function from 1 over x squared to 1 over x, all of a sudden it doesn't work anymore. The thing does what we call diverging. So up here it was converging because we got an answer of 1. We got a finite number for our answer. Down here, 1 over x diverges. Okay, that is, it has an infinite area under that curve. So the further you go down, you move that b down the line, your value is blowing up, and we can see that happening here in our chart where they take different values of b. Notice up here when we did it, our values of b were getting closer to 1. As we extended b down the right axis, these values were getting closer and closer to 1. But down here, when you do it for 1 over x, your values are blowing up and getting bigger and bigger. And that's just going to continue to happen. They grow really slow because the natural log is involved, and the natural log is it's one of the slowest growing functions you can come up with. It's always increasing, but and it doesn't have an asymptote. So you can find asymptotes that grow slower, or functions that grow slower that have an asymptote. But for a function that doesn't have a horizontal asymptote, it's hard to find something that grows slower than natural log. So, you know, the numbers aren't getting big fast, but they will eventually get bigger and bigger and bigger. They don't settle down to a specific value like we saw above. Okay. So that's just kind of weird. If we take the integral from 1 to infinity of 1 over x dx, we end up with the thing diverging, because basically you turn this into the limit as b goes to infinity, right? That's what this up here tells us to do. When you see this thing on the left, turn it into this thing on the right. So that's what we do. We take this integral that we're given, and we turn it to the thing on the right, which is the limit as b goes to infinity of 1 to b of 1 over x dx. Well, when you take the integral of 1 over x, you get the natural log of x, right? So that's where this comes from. So we're left with the limit in front, natural log of x from 1 to b. Well, when we plug those in, we get the limit as b goes to infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0, of course. That just leaves us with the natural log of b, but the natural log of b is always going to get bigger and bigger. It gets big slowly, right? You can take the natural log of, 10 trillion, and that number will be surprisingly small, but if you keep going down that x-axis, that value is going to keep rising. So it's kind of a weird, there's a weird cutoff between 1 over x and 1 over x squared, where 1 over x squared is convergent, that is, it has a finite area. 1 over x diverges, that means it has an infinite area in this way. So it's just kind of an interesting, like somewhere in here, in between these two functions is the cutoff for where, at least for this type, things converge or diverge. Okay? So let's take a look at one of these types of problems. I think there's no point in me rewriting it. I'll just kind of make sure we all talk through these steps, because, this is pretty bare. You might not be able to follow what's going on here. So I'll walk us through this to make sure we really understand what's going on with this problem. And then you're just going to find the ones in the book or in the homework, and you can check back here, match the ones in the book and go, oh, okay, my problem's kind of like this one, and then try to follow along with how the book is working out this problem and try to do the same thing for yourself. And of course, there's the videos that are in there. There's the videos that go along with the problem. So if you need to watch the video, of course, you can do that as well. Okay. But, you know, use the videos when you need them, but try to use them less and less. That means you know what you're doing if you can do it without watching the video. Oh, that's for later. Where am I? Oh, back here. There we go. Okay, so we want to evaluate the integral from 5 to infinity of 1 over x to the 3/2 dx. So we're just given this problem. We're told to evaluate that integral. And so I'm looking at that and go, okay, how do I think about this problem? Well, there's an infinity in it, so then I know it's an improper integral. So that means I sort of go back to this table up here and consult my table and go, okay, is it one of these three situations right here? Yep, it appears to be this first one, right? For us, we were going, what, 5 to infinity? So we are going to set up the limit as b goes to infinity of 5 to b of our function dx. Okay, so that's what this is. We say, okay, we're going to write this as the limit as b goes to infinity of the integral from 5 to b of 1 over x to the 3/2 dx. Okay, so notice we haven't actually done any integration yet. We've just changed this integral into the limit as b goes to infinity of this other one, where our upper endpoint is now b. Okay, so we have the limit as b goes to infinity of the integral from 5 to b. Now we're just rewriting it in that way that we it makes it easier to take integrals when you use negative or rational exponents, because most of the rules that we have for taking integrals are written in the form that tell us what to do with exponents. So that's all that's happening, is they're just writing this as x to the negative 3/2, because that's what this is. This is x to the negative 3/2. That's just a different way of writing it, right? X to the negative 3/2 means 1 over x to the 3/2. Okay, so nothing fancy going on, just that's like we did that in algebra class, right? We write that. Okay, now we actually take the integral. So now we think about this. Okay, so what do I do? I've got x to the negative 3/2. I want to increase the exponent by 1, and then I want to divide by that new exponent, right? So if we've got, we can write that over here. We'll come back to this part later. Okay, so what is our, right, that's what we had there, I think. X to the negative 3/2, right. Okay, so then we want to, what do we want to do? We want to add 1 to the exponent, right? So if we do that, negative 3/2 is negative 1.5. So negative 1.5 plus 1 is negative 1/2, right? So it's going to become x to the negative 1/2 divided by negative 1/2. Right? So that's just our integral rule. We raise the exponent by 1 and then divide by that new exponent. But dividing by negative 1/2 is the same as multiplying by negative 2. Meaning this becomes equals negative 2x to the negative 1/2. So that's kind of how our integration works, right? Raise the exponent by 1, making it negative 1/2, divide by that new exponent, dividing by negative 1/2 is the same as multiplying by negative 2. So that's where this step comes in. That's where the negative 2x to the negative 1/2 comes from. Yeah, I haven't taken roll yet. Someone's asking. I haven't taken roll yet. I'll do it in a little bit. Thanks. Okay, so that's where this negative 2x to the negative 1/2 comes from. If you're wondering, they took the integral, they integrated this. Hopefully, you're all pretty comfortable with that, and you sort of were able to work through that. But that's how that occurred. So we still have this limit as b goes to infinity floating up front. We've now taken the integral, and we have to evaluate it at the endpoints 5 and b, the same endpoints that we had on the integral. Well, then we do that. So we take 5, and we plug 5 in here. So we get, we plug the b in first, so we get negative 2b to the negative 1/2. Gives us this piece. Then we subtract what we get when we plug the 5 in. So this is what happens when you plug those values in. Oops. I hate that it changes the size when you go to the next page. Okay, so, but what's going to happen here as b goes to infinity? Well, remember this negative exponent, that's actually putting b in the denominator of a fraction. Right? This would be 1 over b to the 1/2. So as b explodes, think about what a fraction does. When the denominator blows up, but the numerator stays fixed, that whole fraction is shrinking down to 0. So this first term becomes 0, and this first term becomes what? Minus 1 over the square root of 5? Yeah. So we get negative 2 times 0, because the limit shrunk this term down to 0. No other terms had a b in it. So when we send the limit as b goes to infinity, it only affects the terms with b in it. So this one went to 0. This one ended up being minus 1 over 5 to the 1/2. Simplifying all that, you simply get 2 over square root of 5, right? Because when you distribute the negative 2 in, here you get 0. When you distribute the negative in over here, you get negative times negative is positive. The 2 ends up in the numerator. 5 to the 1/2 becomes square root of 5. So this complicated integral right here becomes 2 over the square root of 5. And the only, like I was saying, most of you hopefully already understand how to integrate x to the negative 3/2. I know it hasn't been that long. We move so fast in the summer. You've only had a couple of days to get used to that. But hopefully you're getting there quickly. The new step is this conversion right here, the very first step, where you change it to being the limit as b goes to infinity of this other integral. That's the new step. The rest of this, like, you already knew how to take limits. That was the first thing we did in the class. And then hopefully you know how to take integrals. That's what we've been doing the last couple days. The new step is just sort of putting those two things together in this form right here. Okay. Right, and here's kind of a picture that sums up what we were looking at. This is that area. I think that's this area. 1 over x to the 3/2, that seems right. Yeah, from 5 to infinity, right? Okay, let me take roll. This is a good spot to take roll. Okay, Juliet, I got you. Okay, got Juliet there. And then, let's see. So, looks like people I'm missing are Trey B, Isabella G, Edson H, Daniel N. So if you're one of those people I just said, get my attention so that I mark you as here, okay? Yep, good. Okay, wonderful. Okay, I think everyone's good then. Yeah, okay, I got Elizabeth. We're good. Okay, just the people I mentioned. If I read off your name, then I didn't get you. Everyone else, it looks like I got. Right, so you can see here in this problem, we're doing basically the same thing we just did, except now they're going to start throwing stuff at you that it's not quite just one step, right? What do we have here? We have a u substitution. So here we have a u substitution in order to do the integral, but it just doesn't really make any difference as far as how, like, I mean, the actual integration, like, you might still be getting used to substitution from, again, in the summer, it's so fast. You just learned substitution 2 days ago. So I get if you're still a little shaky with it, because it takes students, you know, usually a little while. You got to focus on it a little bit to get the hang of it. But this is just a problem where we have to use substitution, except now for this integral, we're going from negative infinity to 1. So instead of going to infinity in the right direction, the positive direction, we're going to infinity in the left direction, the negative direction. So notice how here the integral is now set up. Actually, we'll come back to this part. But we set it up as the limit as b goes to negative infinity from b to negative 1. Right, so we just put the b on the left side of the interval instead of being on the right side of the interval, and this time we send it to negative infinity. So it's the same basic concept that we did in the previous problem. You're just going to the other infinity. Instead of positive infinity, you're going to negative infinity. Right, that's really the only difference. And then, yeah, they made it a little bit harder by making it a u substitution problem. But if you let u be x minus 2, then this problem becomes 1 over u cubed. Your du is equal to dx, so the dx just becomes the du. And all of a sudden, you now have the integral from negative infinity to negative 1, 1 over u cubed, which seems a lot easier to deal with than the thing that we started with. Right, so then again, we put it in terms of the exponent because most of our calculus rules are written in terms of what to do with an exponent. So we write it as u to the negative 3. That's what 1 over u cubed means. And then we actually make this conversion that I just talked about a second ago to the limit as b goes to negative infinity of the integral from b to negative 1, u to the negative 3 u to the negative 3 du. Now here we take the integral, right? So what do? You increase the exponent by 1, so negative 3 becomes negative 2. People kind of make a mistake here. A common mistake is people will do the opposite and make this like negative 4. But remember, we're adding 1 to the exponent because they go, oh, well, 3 plus 1 is 4. No, but negative 3 plus 1 is negative 2. So you have to remember that. So that's why the exponent becomes negative 2. You divide by negative 2. We take the limit of this from b to negative 1. So you plug in your negative 1, you get this term, minus what you get when you plug in b. But this term, b to the negative 2, becomes 1 over b squared, right? So b to the negative 2 over negative 2 becomes, it becomes 1 over negative 2b, but we're subtracting it. So if you're subtracting a negative, that's the same as adding, right? So that's why it becomes a positive. It doesn't even really matter in this case because the whole term goes to 0. But I'm just helping you watch each step so that you can see exactly what's happening. So whether we're adding or subtracting that term, it goes to 0 in the limit, and we end up with negative 1/2 plus 0. So the whole area is negative 1/2. You go, wait, what do you mean the area is negative 1/2? Well, remember, that's how, when we talk about area under the curve, that's how we count area that is below the x-axis but above the curve. This kind of area gets counted as negative, whereas the area above the curve gets counted as positive. So if you're, if you're above the axis but below the curve, like up here, this area would get counted as positive area. This area here that is below the axis but above the curve, that gets counted as negative area. So that's how we have a total negative area. We don't usually talk about that, like when we're saying, oh, what's the area of the carpet in this room? You wouldn't usually give a negative value. But in calculus, sometimes these areas represent quantities. The area might be, like, it's weird to talk about a negative area, but if that area represents like money, then that represents you losing money, right? So the area can still represent a negative thing. Think about it in terms of what the area is representing, not the fact that the area itself is negative. Okay, that's kind of a thing, a weird thing. Okay, now we end up with that double-sided integral. So now we're going, like, we have a really basic function here. It's just x. So the part in the integral is x dx. Okay, that's easy. Hopefully everyone here can integrate x, I hope, at this point, right? But we're going from negative infinity to positive infinity. All right, well, if we go back up to this rule here, we're using now rule 3 on this page, right here. Rule 3, where it says if we have an integral that goes from negative infinity to infinity, we're going to break it up basically into the two types of problems we just looked at. So we're going to break it up into the two previous examples are similar to those previous two examples and finish the problem that way. So that's what we do. So we break it up into the limit as a goes to negative infinity of the integral from a to 0 x dx. So that's basically this piece over here on the left. This area is that left piece over here. A is going to negative infinity, so it's this piece. And then plus the limit as b goes to infinity from 0 to b x dx. That's this piece over here on the right. So we just took this one integral that represents this whole thing, and we broke it up into the piece on the left and the piece on the right. Now, you wouldn't have had to choose 0 to do it that way, but it kind of makes the most sense to choose 0, right? You could have chosen 5 or pi or a billion for that intermediate value. Doesn't really matter what you pick, but 0 sort of seems the simplest to deal with, right? So we use 0, we break it up the left hand, right half. And then, of course, the integral of x is going to be x squared over 2 because x is x to the 1. So the exponent is a 1. We raise that exponent by 1 to get 2, and then we divide by that new exponent. So that's where the divided by 2 piece comes from. So it becomes the limit as a goes to negative infinity of x squared over 2 from a to 0. So when we plug in 0, obviously we get a 0 right here. And then we're going to plug in a, and we get minus a squared over 2. So we're just going to hold on to that for a second. Then we do basically the same game over here with our right-sided limit. Plug in b to get b squared over 2. Plug in 0 to get 0 squared over 2. Subtract them. So these terms are obviously 0. So that's why we end up with the negative a squared over 2 plus the limit of b squared over 2. So what happens when we send this to negative infinity? This whole thing goes to negative infinity. And when we send this to positive infinity, this whole thing goes to infinity. So we end up with negative infinity plus infinity. Now, you can't do that, okay? It's what's called an indeterminate form. And the problem with indeterminate forms is, you know, they don't work. You can't Can't use that because we have different types of infinity, right? So we can't just say negative infinity plus infinity. Well, don't those cancel out and equal 0? And the answer is no, right? It doesn't. So we end up with this integral does not represent a real number. We say that it doesn't exist. So this is an integral that we would say diverges. Okay, this is divergent. Okay, can't add infinities. You can't do infinity plus infinity. You can't do infinity times 2. None of that actually makes sense mathematically because infinity is not a number. So how are you going to multiply it by 2 if it's not a number? It doesn't make sense, right? Right. Other indeterminate forms that we can have: 0 divided by 0, infinity divided by infinity, 0 times infinity, 0 to the 0, infinity to the 0, 1 to the plus or minus infinity. None of those really make sense mathematically, at least in this setting that we're talking about. So you can't really deal with them. There are certain areas of mathematics where you can define infinity to be like a specific thing. But those are very specialized, like very specific areas of mathematics. So you don't have to worry about that. The key is don't go trying to add infinity to itself or subtract it from negative infinity or multiply by 2 or something like that. Okay. So here is another type of issue that we run across, and that is, what if we were trying to integrate up against a vertical asymptote? Okay, so remember when we were dealing with 1 over x squared a minute ago? Let me make this a little bigger, I guess. Earlier, when we were doing the example of 1 over x squared, we were going away from the asymptote. We were starting at 1 and then moving to the right, right? Let me bring that picture back. This is 441. I just want to emphasize the difference here. Here, when we were dealing with 1 over x squared, we were avoiding the asymptote altogether. The infinity that we were dealing with was starting at 1 and sending x to infinity. Okay? So that's one type of improper integral. Another type of improper integral we have is this one, where if you look at our integral, look, there's no infinity in there. We're going from -1 to +1. What's the big deal? Why can't I just integrate and plug those numbers in? And the problem is that in the middle, you have this asymptote, and your values are shooting up towards infinity, and you're sort of ignoring that. Okay? So you can't do that. That's the problem. So that's why it can be a little deceptive when you're not looking at an integral closely. You have to look at yourself at the integral and ask yourself, is there any asymptotes inside? Like, is there a vertical asymptote in there that's a problem? And in this case, yes. At 0, which occurs between -1 and +1, we have this asymptote, and that infinity is going to mess things up. So you can see infinity is becoming a problem for us again, but it's a hidden infinity. The earlier problems we did, it was obvious because infinity was showing up in the problem that you were doing. But right here, when we do this, the infinity is hidden in there, right? It's an issue when it's in there. Right? So basically, how do they get around that? Well, they use that same technique we did before, the integral from -1 to 1 of 1 over x squared dx. We break it up into 2 separate integrals, basically the one on the left side of the asymptote and the one on the right side of the asymptote. And sure enough, when you go through and you do the integration, and then you take the limit, look what's happening. We're plugging in 0 into the denominator of a fraction. Well, that's blowing everything up, right? As the denominator shrinks down to 0, the whole fraction blows up. So that means we're getting a divergent integral in this case because the area is blowing up towards infinity. Okay? And then there's a couple application problems, but I want to move on to integration by parts so that I make sure we say the things we want to say on that. Is there any questions before we do that? Okay. And I'm not trying to scare everyone about integration by parts. I'm just saying it's a little bit of a weird setup. It's basically you got to know the formula, which isn't too bad, and then you got to go through and work on it. So let's see. That's the one we just did. So let's go integration by parts, and we'll close this one. I think we've got. Oh, so here's one. Actually, this is. So we can see this problem is like the one we were just looking at in the book, right? And they'll tell you does not exist. DNE stands for does not exist. That basically means it's divergent, right? Okay. Oops, we don't need that yet. In fact, I want to take this and copy it because we're going to need it again, I think. Okay, integration by parts. What is this? Where's my book? So they derive the formula up here, if you want to check that out. Actually, they derive it right here is where they derive it. So if you want to work through that, you can actually see where the formula comes from. All it is basically you're taking the integral of the derivative of u times v. So remember this. So what is this? What is this u and dv dx and v and du dx? That's just the product rule. Remember for derivatives? So we're taking the integral of a derivative of a product. So that's a lot of these techniques that we work through where, remember, substitution is a special technique we come up with for undoing the chain rule derivative, right? When we're finding the antiderivative of something that we got it using the chain rule, then the way you go back is using the use substitution. So this function comes about, this formula comes about from using the power rule, the product rule for derivatives, okay? And here is basically the formula you end up with. U times v is equal to the integral of u dv plus the integral of v du, which I know sounds complicated, but again, if you write this 30 times and you say it while you're writing it, the integral of u dv is equal to uv minus the integral of v du. You do that 30 times, you're going to have that totally memorized, okay? So the key is, the reason we use this is, what if we have something here in the integral that's really complicated to calculate, but this integral would be easy to calculate? Because notice when you look at the formula, it seems like the right side of the formula is harder than the left side. You're like, well, on the left it's just u dv, and on the right it's like uv minus the integral of v du. That seems more complicated, but the key is sometimes this is really difficult or impossible to calculate, but if we can change it around a little bit, then this integral can be easy. So even though we have a couple more steps to do on the right side of the equation, the hope is that at least we can finish it. We can complete it, whereas over here we might be stuck. Now the good news about this, I kind of mentioned like in the engineering calc, they do just absolutely brutal problems of this nature. You know, one problem can take you 30 minutes to work through, and hopefully you didn't make a mistake in it. At least when you're beginning, they can take you that long. Here, we just use a few basic ones. So you're going to see a pattern. You're going to see these ones where it's x to a power. Let me blow this up. X to a power times natural log of x dx. Now let's look at the homework. Let's shrink this down. Right? That one's a little different. Here we have x to the power times natural log of x, right? Is it? Let's see, right? X to a power times natural log of x, and then sure enough, we're seeing that in the homework. X to a power times natural log of x, right? So what I'm getting at is there's only a few different forms that these things show up in. So if you're stuck on one of these problems and you watch the video and you're still stuck, try to find an example in the book that is similar. Right? The video should be pretty helpful, but try to find one that's similar to what you're doing. Okay, yeah, gotcha. Okay, so here's the key. We're starting off with the integral of x to the fourth natural log of x dx, but we don't really know how to solve that. I don't know how to solve that, right? How are we going to do that? So our goal is to put this integral into something equivalent using this formula. Basically, we're being given the thing on the left, and we want to turn it into the thing on the right because this integral is then going to be something that we know how to integrate. So what the whole thing here, like you'll see this, once you get used to this, it's really about picking the right values for u and dv, okay? Because that's what your integral is. It's given to you in the form of u dv. So you're going to look at the problem you were given, and you're going to label one of these pieces u, and you're going to label one of them dv, okay? And that choice is going to make the problem either hard or easy, sometimes impossible or easy. I guess sometimes it could be hard or medium. I'm not saying they're all going to be super easy, but it'll change the problem into a it'll change it into something that at least should be doable. You can like work through it. But if you make the wrong choice of u and dv, it isn't going to work. Okay, so that's why it can also be helpful to look up these examples in the book, is if you're having trouble and it's not working, you might be making bad choices for u and dv. Or if you come in here and go, oh, I see, they're saying that u should be natural log, and I was making ux to the fourth. That's my issue. Well, then now you know how to switch it around and make it work, right? The thing is, there aren't that many choices. So if you're trying it one way and it doesn't work, just switch it around and try it the other way. There aren't that many things to pick for you. It's basically x to the fourth or natural log of x. So if one isn't happening, switch to the other. So they're saying we'll let u be natural log of x. That means dv has to be whatever's left over. So if u is natural log of x, the leftover is x to the fourth dx. Okay, so basically once you've picked u, everything else is like determined. Okay, but there's 4 pieces. Now I would encourage you to write them down. See how I did here? I would encourage you to start every one of these problems, especially in the beginning when you're just learning how this works. Start by writing out the formula. The integral of u dv is equal to uv minus the integral of v du. Right? Write out the formula and even say it while you're writing it out, and you will have it memorized in no time, right? It's not a super complicated formula, but if you're saying it and you're writing it every time you use it, the thing will just naturally be memorized for you. Then what you want to do in order to plug the things in here, what do we need? Well, we need a u and a v. We need a v and a du, and we need a dv. So basically what you want to do is write these 4 values down. Once you've figured out what your u is, right, that's from your original problem, the leftover is the dv. So you've got your u and your dv. Well, once you know u, you can get du. And once you know dv, you can get v. Okay? So really it's just a matter of u, and then everything else kind of falls into place. This part right here, I see people all the time try to do this step without writing it. And hopefully you're sort of picking up on the fact that I mentioned that like students try to do these problems without writing things down. You're not going to do them in your head. Maybe when you're like an ace at this and you've like done a bunch of these problems, then you'll be able to look at them and go, oh, I know how the breakdown should work. But in the beginning when you're struggling, you should be writing everything down. Okay? Students will say, oh, I don't know how to do this, and then there's like a blank paper in front of them. That's because you're not writing anything down. Write down the formula. The formulas you should always write down. They are your roadmap through the problem. So of course you should be writing them down, right? That'd be like having a map with you, but it's, or your GPS, but your GPS is in your trunk and you're trying to drive around. Well, the GPS isn't going to do you much good if it's in the trunk, right? So write down the map that gets you through the problem, the formula, and then write down the 4 pieces that you're going to plug in there. If you do that, the problem just sort of, for the most part, just kind of falls out. So we let u equal natural log of x, dv equals x to the 4th dx. So that means that du is going to be 1 over x dx, right? Now, so where did that come from? What am I talking about? Well, remember the 4 pieces that we need, u, du, dv, and v. We picked u and dv. Well, if u is natural log of x, then du is the derivative of that. So what's the derivative of natural log of x? 1 over x dx, right? So once you decided u, the du is, you just take the derivative and you get this piece. Okay, where did this v come from? Well, if dv is x to the 4th dx, then that means we need to integrate this part in order to get it. So we take the integral of x to the 4th dx to get x to the 5th over 5. So you just integrate. Raise that exponent by 1, divide by that new exponent. So x to the 5th over 5. Okay? So now we have these 4 pieces. So kind of how I have them laid out here, u, du, dv, v. We've got them labeled here, u, dv, du, v. So you've got your 4 pieces. They just have it written differently. Now substitute it into your formula. The integral of u dv, that's what you started with, will be equal to u times v minus the integral of v du. So you've got your u here, natural log of x, your v here, x to the 5th over 5, minus the integral of v, x to the 5th over 5, du, 1 over x dx. So you can see all 4 of these pieces up here are fitting in our formula somewhere. We've got our u, we've got a v, a du. The dv was in the original problem. So writing them all out, and then once you have them written out, you just plug them in there. And one thing that's nice about this formula is half the formula isn't even an integral, right? Look at this first part. It's just some algebra right there. So we have 1/5 x to the 5th natural log of x. Okay, nothing to do there. Then we have this integral over here. We pull the 1/5 out front. Well, the integral of x to the 4th dx is easy. In fact, we already did it once in this problem, right? So you're going to raise the exponent by 1 to get x to the 5th, and then divide by 5. And then, of course, we have to remember to add the plus c on the end because we are doing an indefinite integral. Okay, so simplifying all that down just becomes this thing at the bottom, and that's good to go. So the key here is this: look at the integral we started with, the integral of x to the 4th natural log of x dx, and we go, I don't know how to solve that, but look at the integral we ended up actually solving. We did a bunch of algebra, but the integral we did was just the integral of x to the 4th dx. That's much easier, right? That's like our most basic integral that we know how to integrate. Maybe not the most basic. I guess integrating a constant would be a little more basic, but that's pretty basic on our hierarchy of functions that we have to integrate. That one's pretty straightforward. Okay? And then you just simplify things and you end up with with your answer there. Okay? And then you can see now we have another form. Evaluate the integral of x e to the 4x dx. And you'll see problems in the homework that look like that. So you'll see here like, which form was it? X e to the 4x. Here we have x e to the negative 8x. X e to the 5x, so another homework problem that looks like that one. So that's 2 that kind of take on this next form we're looking at. So that's what I'm saying. You can take the homework problem you're looking at and of course watch the video, but then try to find the example in the ebook and then just follow along with what they were doing. So here, this is a case where it works out pretty well either way when you make your substitutions. So they're saying if we let u equal x and dv equal e to the 4x dx, we're gonna be okay, because both of these things are easy to integrate and easy to differentiate, right? Because when you pick your u, you differentiate it to get du. When you pick your dv, you integrate it to get v. So sometimes you want to think about, like, well, which part is easy to integrate and which part is easy to differentiate. But in this case, they're both easy to integrate and differentiate. So you're actually good. You can do it both ways. So you let u equal x and let dv equal e to the 4x. Now just be careful here. Your du becomes dx, because when we differentiate u with respect to x, we just get dx, right? So there's how they figured out the du. And then over here, we say dv is equal to e to the 4x dx. So v is equal to the integral of e to the 4x dx. Well, just think about your, I mean, you could do it as a basic substitution if you needed to, but you can also just check, what if we took the derivative of 1/4 e to the 4x? Well, we would end up multiplying by the derivative of the exponent because of the chain rule. Multiplying 1/4 by 4 cancels those out, and you're just left with e to the 4x. If you don't remember how to do this, just do it's one of the simpler substitution problems. Just do a basic substitution there. Okay. So now when we substitute in, we've got our u, our dv, our du, and our v. You just plug them all in, and you can see, sure, this thing looks really complicated, but the stuff in front, we don't really have to worry about. It's just algebra. We're not like integrating this term. Minus the integral of 1/4 e to the 4x dx. You bring the 1/4 out front. The integral of e to the 4x dx is pretty easy. We actually just did that a moment ago. You end up with this, and you end up with your answer. Okay. Here's one that is not always obvious that you would use this, because it doesn't seem like there's enough pieces, right? Most people go like, well, I need a u and I need a dv, but obviously integrating natural log of x would be really helpful, right? Some people get confused with natural log of x, and they're like, no, the integral for natural log of x is really easy, but they're thinking of the derivative. The derivative for natural log of x is easy, right? It's 1/x. But when you look at this, you don't necessarily think, oh, I should do integration by parts, because you're like, there's no parts. There's just the one thing, natural log of x. But we could view this as being natural log of x is one piece, or one part, I should say, and then the dx is one part, right? So the integral can be viewed as the product of natural log of x and dx, and therefore we can use integration by parts. So we let u equal natural log of x. We let dv equal dx. Well, then du is going to be 1/x dx, because the natural log of the derivative of natural log of x is 1/x dx. And then when we integrate dx, because we're integrating, if we take dv is equal to dx, so if we integrate both sides, v is equal to the integral of dx, well, that's just x, right? So this one's actually pretty simple to plug everything into. We end up with the integral of natural log of x dx. Our u and v become natural log of x times x. Don't make this natural log of x squared, right? It's natural log of x in parentheses times x. So this x really should be written in front, like they do down here, to not cause confusion. Minus the integral of x times 1/x dx, because we've got the integral of v du, but our v is x, and our du is 1/x. So look what happens. Our x and 1/x cancel each other out, and we're just left with the integral of 1 dx. Well, when you integrate 1 dx, you just get x. So the integral of natural log of x dx equals x natural log of x minus x plus c. So it's a little bit complicated. It's not a super hard problem, but it's a little bit complicated. You know, people tend to think, oh yeah, natural log, that one's easy. The derivative is easy. The integral takes at least a little bit of work, a little bit of doing. You have to know the formula in order to make that work. Okay. So then we get into some basically some word problems here. So let's see. So what you want to do, like if you're getting stuck with some of these, 5.6. The two main things to do are to watch the video on here. If you're stuck on a particular problem, watch the video and then you know, check the ebook. Try to find a problem that looks like that. These don't all of them have corresponding problems in the video, but they do have in the ebook, but they do have the video that goes with them, right? So if we watch the video here, you can see she's going to do the she's just doing that one. Doesn't seem right. Right. So like here in this one, you could write this one as, actually their video there is not exactly showing a similar problem. Let's see. Think about ways that you could write things in a different way. So remember we talked earlier, I talked to you about writing things in a way, in calculus, we like to write things in terms of the exponents, right? So when you see something like this and you're like, wait, I don't know how this is supposed to work, think about it in terms of writing it as x to the -8th times the natural log of x. Okay, because then you'll see that there's really two parts to the problem, and then you can make a decision about which part you want to write in which or like, you know, try it one way, see if it works. If it doesn't work, try it the other way. Right. Yeah. Okay. So let me see here. We got through that a little faster than I expected. So give me a second to see something. Oh. Let's take a 5-minute break. Okay, let's break for 5 minutes. All right, looks like we're back here. So that lesson went a little quicker than I thought it would, so I just misjudged the time there. So just keep in mind for the integration by parts, like I say, it looks like they have a few other homework problems that are sprinkled in from other sections. They're not all necessarily integration by parts problems, so feel free to, use whatever technique you need to do to get that problem done. But you try to match the problem that you're doing up with the ones in the book that we went over, and go from there. So I think with the time left, I'm going to go over 6.1 so that you can get a start on 6.1. Because I think some of that stuff next week is going to a couple of those sections are going to take some more like a deeper explanation of, and then also I don't want to be teaching you everything on Thursday of next week, because then some of you have already taken the test, right? So we want to get through some more of that in case some of you are taking it. Some of you might take the test Monday or something, right? So let's talk about area of regions in the plane. This one is actually kind of a cool idea. I think it's kind of neat the way it works. If you understand what we've done up to this point and you understand this connection between integrals and areas, this part actually is not very difficult. You just have to make sure you're doing things in the right order. Doing things in the wrong order obviously doesn't work, and then there's a couple of little details. But by and large, if you've followed this chapter so far, or chapter 5, you should be good. Okay, so remember what we have here. Let me move this over a little bit. Like that. So if we take the integral of this function from a to b, what that really means is the area under the curve from a to b, right? So we have the function, the area under the function from a to b. The integral gives us that value. Okay, well, what if we wanted to figure out the area between two curves? How could we do that? How could we figure out the area that's between two curves? Well, this picture gives us a pretty good indication. If you wanted to figure out the area under this, or between these two curves, you could figure out the whole area under the top curve, right? So both of these colored regions is what you'd get if you took the area under the curve here. This integral up here would give you this whole area right here. And then if you calculated the integral down here, that would be the area of this curved white piece. If you subtracted that off from the big area, well, that would leave you with this pink area right here. Right? So that's where this formula comes from. It's actually not too bad. It's the area is equal to the integral from a to b, right? Those are your two endpoints, of the top function minus the bottom function, because integrating the top function gives you the whole entire area. Integrating the bottom function gives you this lower white area. When you subtract them, you get this pink one in the middle. So from a conceptual standpoint, it's actually pretty straightforward. Right? There's nothing real fancy going on here. You're calculating two areas and then subtracting them. That's all that's really happening when we do this. So that's basically what we do, right? That's basically our formula. The area is equal to the integral from a to b of f of x minus g of x dx. You just subtract those two integrals. Now you want to make sure you know which one you're subtracting from which. If you subtract them in the wrong order, you're going to get the wrong answer, and it's not always immediately obvious which one is which. So you have to make sure that you have the curve that's on top is the curve that comes first in this formula, and the curve that's on the bottom, the lower curve, has to come second. Now, there's times when that can get a little bit messed up. What if the curves cross each other? Well, the answer is then you have to split it up into two separate integrals, right? So that's why they say here in the formula, if f of x and g of x are two continuous functions for which f of x is greater than g of x on some interval, meaning f of x over this interval is always taller than the g of x is, then the area bounded by the two functions and the vertical lines x equals a and x equals b on a to b is this following formula right here. Okay? So this is one you don't even have to spend a lot of time memorizing. You can just sort of think about it and go, oh, well, he kind of explained that if we just subtract these two areas, so that makes sense. It would just be the big integral minus the little integral, and you go from there, as long as you're taking the time to figure out which is the tall function and which is the shorter function. And if you need, you have a graphing calculator available to you, so you can go through and figure that out. So, and you do have so I want to be specific here. You do have a problem like this on the final. You have a problem that gives you two functions. It says find the area. Find the area between these two functions. So they kind of have the picture here, right? So they have you going from 2 to 5, right? Find the area bounded by the line f of x equals 2x plus 5 and the curve g of x equals x squared minus 8x plus 21 and the two vertical lines x equals 2 and x equals 5. Now, this one has this nice picture here, but you're not going to have that picture in the homework problems, right? Notice in the homework problems, they don't give you that. They tell you, like, they want the area bounded by the functions f of x equals x plus 6 and g of x equals e to the 0.5x and the lines x equals 0 and x equals 3. So you have to come up with that picture on your own, which isn't hard to do. You could do it with Desmos, right? If we go Desmos, let's see, is it on here? There we go, Desmos. So just grab Desmos and put them in here. Oops, I'm grabbing the wrong. Too many windows open now. I'm grabbing them all. So we have what? We have the function x plus 6. So you just go, okay, y equals x plus 6. Okay. And then g of x equals e to the 0.5x. And then you can start to kind of see the area that's bounded here. Let me move this over a little. Okay, so we can see that bounded area. And then they say the lines x equals 0 and x equals 3. So let's put those in there. X equals 0 and x equals 3. Oops, x equals 3. So they're talking about this piece right here, right? It's bounded between these two functions, between x equals 0 and x equals 3. So this weird shape right here, that's the area that you have to, that's the area that you have to find. Okay, well, how do you set that up? Well, the x equals 0 and x equals 3, that's the region we're going to be integrating over. So you're going to integrate over that region. So those are your endpoints of your integral. And then you have your two functions, and you have to figure out which function's which. Well, it looks like our line is the one that's taller, and our e to the x curve is the one that's shorter down here. So then we make sure to use the line first. So it's the line x plus 6 minus e to the 0.5x, the integral from 0 to 3. So that's how you would do like this first one right here, this first problem. So I just wanted to point out, because it looks easy, like here in the book where they're working through it, but that's because they have already given you the graph, right? We already have the graph presented to us. You have to create that yourself. So and on the graphing, the TI-84 graphing calculators, if you're using one of those, it's trickier to make vertical lines. So you're kind of going to have to like imagine the vertical lines, but you could put the line in the curve and then just know what region you're integrating over, right? But so that's the way in which they got for this one. You know, the line's on top for this one, the curve's coming up from the bottom. So notice they have the line minus the curve. The integral goes from 2 to 5. That's the endpoints that we're dealing with. And then from there, it's just using the integrals that you learned in chapter 5, right? You're just going through and calculating those areas. So you combine your two functions. Integrating a polynomial is pretty straightforward. Be careful when you're evaluating because you end up with these fractions. But then it turns out the area for this one in the book is 18, right? So the trick is to just make sure you've set up this integral correctly, get the endpoints, get your functions in the right order. If you get them in the right order, it's not going to go well. Okay, in the wrong order. If you get them in the wrong order, it's not going to go well. Okay. Okay, so here's one that's, and I'm trying to remember, believe you do have a homework problem like this. Yeah, so here, see this homework problem here? Let's take a look at how to do this one. This one says, find the area completely enclosed by these two functions. Notice how they didn't give us those endpoints. In the problem that we just worked through a moment ago, it said, and between the lines x equals 0 and x equals 3. And that gave us our a and our b, our upper and lower endpoints of integration. But in this problem, they're not doing that. We have to figure out those endpoints of integration. So let's take a look at how to work through this one. Okay. So they say the area completely enclosed by x squared and square root of x. So where did Desmos go? Did I close it? Nope, good. So what is it? X squared and square root of x. Those are our two functions. Okay, so look what happens when I graph those. Let's go ahead and make this bold. Okay, so let's zoom in here. We can see there's no other bounded area. By bounded, that means enclosed, right? Like think finite area. If we tried to find the area in here in this parabola, it's going to be infinite, right? Same as like over here. This area is infinite. This area is going to be, that should be infinite. Yeah, that would be infinite, right? So the only area that's bounded between the curves is this area over here. So let's zoom in and look at that. Okay. So I can look at that and figure out my endpoints of integration by looking at it. It looks like this region right here that's bounded starts at x equals 0 and it goes to x equals 1. Well, there's my endpoints of integration. So we're going to integrate. Let's see, which one's the top function? Looks like x squared, the red one, is our top function. Sorry, did I just say that right? Square root of x is our top function. X squared is our bottom function. They intersect over here at 0, and they intersect over here again at x equals 1. So that means that our integral that we use to calculate the area between those two curves is going to be the integral from 0 to 1, right? Because we're integrating over x. So from 0 to 1 right here of square root of x minus x squared, and then just do the integral. Once you get that, once you calculate that definite integral, you'll have the area between the two curves. Okay. And you have a couple like that. Here they have another one. Find the area of the region completely bounded by these two curves. So you'll graph them and just see where the endpoints are. I'm trying to remember if they give you ones where the endpoints are kind of messy or if they're pretty straightforward. So let's graph this one and see. It looks like they're still using pretty nice intersection point. So here we get a, oh, sorry, I don't have it on the screen here. This is what that other one looks like. And see, if you go, if you're on Desmos, you can, if you click over here, they'll tell you that intersection point. So it looks like the intersection point happens at an x of -2. And this other one happens at an x of +2. So you would integrate from -2 to +2, the blue function minus the green function. And then you would go from there. If you ever don't know, like if you can't tell by looking at the graph where the intersection points are, the way you get the intersection points is by setting the two functions equal to each other. So worst case scenario, set these two functions equal to each other and solve, and you're going to get 2 and -2. Okay, so you can always do it that way, but it looks like they're using ones that come out really nicely. Looks like for all, at least for all of these. Let's see. Let me double check the third one. So let's see for this one. Yep, coming out pretty nice again. That looks like, okay, but notice there's a complication here. Let's see, did I get that one right? X plus 19 and x cubed minus 3x plus 19. Okay, notice there's a complication here. So what happened? Well, they want the area. Find the area of the region that is completely bounded by the two curves. Well, that would be this area plus this area over here. But we have a problem. In this area, the purple function is the one on top and the black one is the one on bottom. Over here, the black one is the one on top and the purple one is the one on bottom. So even though the endpoints are still easy to read, we can't just integrate from -2 to 2. They might even cancel out and give us an area of 0. It looks kind of symmetric, but I'm not sure if it is or not. But what you have to do is break this up into two integrals. This one over here, and then this one over here. So you would integrate from -2 to 0, the purple function minus the black one. And then you would have a second integral where you integrate from 0 to 2 of the black function minus the purple one. Because you have to make sure you take the top function and subtract the bottom function. Otherwise, it's not going to work right. Okay. Where am I looking for? Right. So that's the next thing they show in the book. If we're going through the book, is they show us the stuff I just showed you about where they don't give you the endpoints. And see what they did here? They set the functions equal to each other and solved. So sometimes if the values are nice, you can get it just by looking at the graph and you can figure out what those endpoints are. But the very worst case scenario, you set your functions equal to each other and solve, just like we did in, you did this in algebra class, right? Back in algebra, set your functions equal to each other and solve them, and you're good to go, okay? But the graph can kind of help you shortcut that a little bit if you have the graph there, and then you do your thing. Right. So this is like the one we were just looking at, where you have the two different regions that I was just talking about, and look what they did. They broke this up into two separate functions, from -4 to 0 and 0 to 4. Sorry, two different integrals. So that's what you have to do when you do that part of the problem. Okay. Now, why would you ever want to find the area between two curves? There's lots of reasons, right? If we were, like, if you're convinced that finding the area under one curve is valuable, which hopefully you've seen enough problems now that you're convinced is helpful, then finding the area between two curves is not much of a stretch to figure out how to make that work. One example that they don't use in this book, but we used in the last book that we used for this class, that's way more expensive. That book was ridiculous compared to this. That book was like $250 or something like that, and the program had all sorts of technical issues with it. But one of the examples they went over is what's called the Gini index. You can look that up if you want. It's GINI, the Gini index. And basically what it is it's a measure of inequality. So basically you come up with a graph that represents or a function that represents the level of inequality, and that level can vary depending on this Gini index. And what you do is you compare that to the line y equals x, and the more area between the curve and the line y equals x represents more inequality, right? So you might hear, like if you're paying attention to this kind of stuff, you might hear where they talk about how society is becoming more and more inequality. Like basically since the 80s, you've just seen poor people are getting poorer, rich people are getting richer, and it's sort of getting dragged out in either direction. Well, how can they say that? How could you really say that inequality is worse than it is in the 80s? Well, you use something like the Gini index, and you can and you model the function to represent 1980. You model the function to represent 2020, and then by using by subtracting by finding the area between these curves, you can see the difference, how much more inequality there is now. Like I'm talking about like money-wise, right? For like income inequality, how much more inequality there is now based on compared to say 1980 or something like that. So, you know, you hear these things on the radio or, you know, NPR or whatever, there's talking about these things, but there's actual math behind it usually backing this kind of stuff up, so you can back it up with actual critical numbers, and the way in which you do that involves finding the area between two curves. Okay, so there's all sorts of different reasons why you do this. If you follow the stock market or anything, the stock market people like to talk about indicators. Oh, this indicator is up. You know, you talk about durable goods or housing starts or different kinds of stuff. You want to check how those things are changing over time. You can use the area between curves, and then people make decisions. Oh, we should invest in real estate because the real estate market's going to expected to explode next year or something like that, right? So these things get used in various different situations that can definitely be useful overall. So we're going to stop there. I'll start next week with, we'll continue with chapter 6. Keep working on stuff. Make sure you're doing the homework. Finish strong, right? Use this weekend to get yourself as caught up as you possibly can. Get yourself ready for that test. Form a study group. Go to the tutoring center, whatever you need to do. Make sure you have your testing center appointments set up, and you're all good to go with that kind of stuff. Yeah, and we'll see you on Tuesday then. Okay? So I'm going to shut down the YouTube stream. Anyone who wants to come chat with me in Zoom, feel free to do so. Okay, bye.